and Professor Paul Bush, who are no longer with us. COVID is a terrible time, and during this period, many other illnesses also have cropped up because of one reason or other. Many of our young colleagues and many of our valued colleagues are no more. One of them is Professor Hema Ramachandran, as you saw in the morning afternoon. Professor Poonam Mehta was talking about her work with Hema. Many of us know her. So I'd like to request Poonam to say a few words about Hema and maybe share some of the experiments which she could not show at that time because we hurried her. Poonam can speak about her.
Yeah. So should I share my screen or what?
If you want to, otherwise you can tell in words.
Okay, I can probably tell it in words.
Yeah.
So I mean, my interaction with Hema was during my postdoc period while I was at Raman Research Institute, and in fact that is the place where I picked up this my interest in geometric phases. So with Sam and Supurna, we came up with an idea in the context of optics, and that was a theoretical proposal. Basically, it was related to the context of intensity interference, and which was the work of Hanbury, Brown, and Twiss in 1950s. And they actually did it in the context of measuring the diameters of angular size of the star using intensity interference. And there was problem with amplitude interferometry, and so Hanbury, Brown, Twiss, their work became very prominent. And then, so related to that idea, what we thought was in the actual original idea, there was no mention of, there was no this spin degree of freedom. The vector nature of light was not being used. The polarization was, it was basically with unpolarized light you have. So the main catchy thing there was you have incoherent source. So usually in the interference experiments, one talks about laser light, and there it was incoherent source. So with the incoherent source, there were cross correlations that showed some interesting effect. And in that same setup, we proposed that if we use polarizers, there was this very small modification in that setup. However, the consequence was very, very interesting. So there was this completely new contribution in the cross correlation, which was not present in the lower order correlations. So higher order correlations had imprints of geometric effects in the intensity interference context. Now, as I said earlier, all these effects can be seen in a variety of systems. So in the optics context, we proposed this, and we did a quantum field theory calculation there. And using that same idea, we wanted to do the experiment, and that's where my interaction with Hema came into context. And it was it took almost like 2 years to actually get it working. So initially we tried implementing the same ideas that we proposed in the theoretical, but somehow there were challenges in implementing it. But Hema, being, I mean, she usually comes across as a, she used to come across, I mean, I have to use past tense for her, it's very sad. She, if you think about Hema, people who have interacted with her will always remember her characteristic smile. I mean, her composure and the smile. That's something which probably everybody who came across would remember distinctly. So she was a very firm person, very warm, very gentle, usually a reserved person, but she was very strongly driven. So she didn't give up, and we used to have interactions once in a, so one thing failed, then we, but it was something, so she did not leave it. That was what I would say. She was very driven. That is what something which was very inspiring for me to see. And yeah, I mean, of course, these days, nothing is certain. And as Professor Panigrahi said, I mean, we are losing so many of our colleagues, family members. It's really very devastating. Hema's also other thing that I would like to mention here is that her role in the national mission on quantum information, quantum technology, and application. I think her role was very pivotal there as well. I mean, as our DST secretary, Professor Ashutosh Sharma says that, I mean, she was a gem of exceptional brilliance, really, because not only because of her scientific contributions, but also in her rather extraordinary commitment to this national mission without any self interests, even while going through these tough times in her life. I mean, it is really remarkable. So her devotion, her dedication, her passion for science, I think that is really to be appreciated and celebrated and imbibed for youngsters, for all of us. I think that is something which keeps us going. So yeah, I think probably that's what I would like to say. May her soul rest in peace, and yeah.
Thank you, Punam. Thank you, Punam.
Thank you.
We have Dr. Ashok Udagiri, who has worked with Hema on pole atoms. You talked about persistence. Ashok is one more person who is going to talk about persistence of Hema. Ashok,
yeah. Can you can hear me?
Yeah, we can hear you.
Yeah, good. Hi, I'm Ashok Udagiri. Right now I'm in University of Hyderabad. So just before joining here in 2006, I was also a postdoc with Hema Ramchandran. At that point, she had proposed building of a BEC system. And of course, it was kind of a collaborative program, but 3-4 groups doing independently. Professor Unikrishnan in TIFR, who finally managed it, and Vasant Natarajan and Hema, all of us were trying to achieve our own BEC setups. Again, considering the fact that Hema's original training was in high pressure physics, nothing, I mean, as far away from optics as possible, but it was kind of inspirational in the way over the years she had picked up all the nitty-gritties of an optics-based research, and had set up a laser cooling. Of course, the team at that time was Andal Narayanan and Hema Ramchandran, and Professor R. Srinivasan, who is traditionally a low temperature physicist, also came into this laser cooling, and together they had achieved a lot of things. And by the time I joined as a postdoc, there was already a full-fledged magneto-optic trap working in the in Raman Research Institute. It was more of a double thing, and initially their lab was a cramped 4 feet by 4 feet thing in the basement below library, but at that time they were building one more building. Raman Institute has it's a part of Raman's will that there cannot be more buildings in the place, so there has to be some ratio has to be maintained. So this was kind of what was actually a water tank, but below that there was a lab space kind of a stuff. And so she was obviously involved in that also. I mean, the designing of how the entire optics group will have enough lab space over there. So it was juggling administration, juggling science, and also a very interesting work that was going on simultaneously in the next lab, which was a continuation of what, not exactly continuation of that, but more of depolarization of light that happens when things go through random media. More of it she worked later also, and how to extract information about it. The reason I mention it is now I'm involved in some other work where I'm picking up some of the ideas that time Hema had published. It would have been nice if she was around and we could still discuss a lot more with that. So it again, as Poonam Madam mentioned, it's all of the same, pretty much the same things which inspire all of us, is the perseverance with which she went on with the thing. And it was a quiet working nature where not really pressurizing anyone, not making anyone tensed up, but still trying to push people to get work done, and managing a whole team of people, trying to tell them what to do, how to go about. And in between there would be some uh, interesting other discussions, but also really getting into the science part of it. I mean, more and more of science. It was basically enjoying the science that we did was what made me really appreciate that whole. My I spent 3 years in Raman Institute before I moved on to Hyderabad, and those 3 years were really enjoyable because of these reasons. I mean, any scientific thing would be of interest, and it would go on for a long discussion, breaking down it into essential parts. And so on all the related startup where we did a little bit, dabbled a little bit into quantum information and how to use it. Of course, it was all the beginning parts for all of us, so everybody were learning. So that was where did learn a lot, and also a lot of work, hard work went into experimental science, where getting a BEC. Finally, we did not get BEC in that lab. Of course, as of now, the only running Bose-Einstein condensate lab in the country is of Umakant in ISER Pune, but a lot of things did go on. A lot of optics-based research go on, and cold atoms and related stuff with it. It was an enjoyable science part of it, and definitely it's a loss because we do know that she was part of many decision-making things also. And later on, when I started a project which we did, it was again an initial project on quantum cryptography part. She was one on the other side of it. Now she was a part of the steering committee of that project. This was through DIT, and a lot of very important suggestions of how to go about were given to me, which was useful in making that project also. So that's what I would like to say.
Thank you, Ashok.
Right, yeah.
Actually, I would like to narrate a small incident, about her personality. It was indoor, quite some time back. That was this leather symposium, this annual leather symposium. And my wife, Asuna Pradhan, she was giving the talk. And in that auditorium, children were not allowed. And in fact, security was very strict about that. So my wife's student, Maya, who is now a faculty in IIT, Roorkee. So her two children and my son, I was kept in charge of them. So I was sitting outside. Then I heard the talk started. Professor Aurora was giving a talk and Emma was giving a talk. So I could not resist. Somehow I had to get in. So I told these kids that here are small chocolates for you. And if you keep quiet, then you will get more rewards. So I could convince the guard to allow me and these three kids to the last bench, and we were sitting very quietly. Then Professor Aurora's talk, of course, went on some theoretical aspects, solitons, things like that. His work with Everly on lambda system. And then after that got over, Hema's talk was about light passes through turbid media, as Ashok was pointing out. And, she showed it how through polarization getting, how, and I think some time getting also, how, you can actually remove the noise. And she put a coil into some milky stuff. And then once the imaging was done, you could see the coil. Before that, coil was not visible. And the kids were all excited. And after she came out. And you see, for example, people like Professor Aurora were telling Hema that was a good talk. And these three kids, they got very excited. They went, "Auntie, we loved your talk." And she was sort of perplexed. Then she said, "We were not able to see the coin. Oh my God, the coin looks so nice. Can I see the coin?" And you can see in her, she's the exert personality. So there was this smile which spontaneously came out of her mouth. The three kids are enjoying her science. So that was Emma. Last time I saw her, she was taking long walks in RRI, and we wished each other. But anyway, these things may have soul rest in peace.
Yeah.
Thank you, Punaman, also for sharing your experiences.
Yes. Yeah.
Thank you.
Thank you.
Yeah,
Now,
also, can I just add a comment?
Sure.
I think in the Raman Institute, Hema was probably the first person in the optics group, right? If I'm not wrong. So probably developed after. I mean, now there are so many people there in the light and matter physics group.
Yes.
But probably earlier,
yes.
It was.
If you keep aside the Pancharatnam phase guy, why do I forget his name?
Bhandari.
Bhandari. Yeah. So Rajendra Bhandari, who was more of a theoretician. Hema was the first one to start experiments in Raman Institute. And it's kind of interesting because she had just come out of BRC and
a very different thing, very different background. Yeah.
Totally different. I mean, she was more in a high pressure division. And but then apparently it was a challenge thrown to her to set up an optics thing, and she said she could do it and convince the people, and she was in it. Yeah.
In the context of her workshop, if I remember correctly, also correct me, she had an experimental paper on this control knot implementation through dipole blocking, right? Yes.
There's a control knot implementation. Yeah, but see, most of it. It's kind of amazing how she picked up both the theory. I mean, both she and Andal Narayanan came from a condensed matter group. Andal was doing some liquid crystal thing. And some of the things that it took us quite some time to pick up all the density matrix formalism, the way we calculate everything. She could just pick it up very fast, and there are quite a lot of papers on that also. You remember that there is that... it's not a 2BEC. It's a 2BEC thing, I think. They're looking at Graspetovsky equation with psi 1 and psi 2. Two-component BEC. As I said, again, finally boils down to a density matrix kind of calculation. So they could really do a lot of things. And yes, most of the initial experimental setup was in light scattering. By random media. A lot of work was done in light scattering by random media. There's this with this guy who's now in TIFR.
Majumdar.
Sushil Majumdar, who's our first student. And then there was also one more person who came from IISc engineering department, Umesh. His PhD was in IISc, but he was a co-investigator of the project. Right. So a lot of random media work was done. Divya, our third student, and a lot of it. And then side by side...
Professor Khare, welcome.
Okay. Okay. Yeah. So, then it came up, and yes, as you said, there are now a lot of people who joined in later, but she was the first one to start off light matter interaction group.
Good. Also, we will have a few minutes in the memory of Professor Paul Bose, a very eminent quantum information person who passed away. I now request Dr. Alok Khan to share a few words about his memory with Professor Paul Bose. Professor Khare, welcome.
Yes. Okay.
So we just had a small, session kind of thing on Hema Ramachandran's work because she's no more.
Oh, I see. Okay.
So then Professor Paul Booth, who I knew and Alok also knew, he also passed away, unfortunately. So Alok is also going to say a few words about him. Alok, are you around?
Where is Alok?
Alok is supposed to be around. Let me just. Alok said he will join. Let me see. But anyway, let me. I-55 we have said. There are these generalizations of uncertainty relation due to Ozawa, who gave a talk here, and then Paul Booth had, his version of it. And you see, if you look at the uncertainty relation since the work of Kendall and Heisenberg, Schrödinger and Robertson, significant things have been added to it in the term of uncertainty while measuring, uncertainty while preparing the state, uncertainty due to back reaction. A lot of those things are there. And Paul Booth has played a very significant role. You see, large number of publications about this very simple thing called uncertainty. And, he visited Patna and gave a series of talks. Professor Paul Booth Professor Ozawa also visited Patna. So while passing, Professor Paul Booth passed through Calcutta, stayed here for 2 days. And while we were doing some work, I showed him about, this uncertainty relation which we had worked on. He was so happy that he said, you send it to Foundations of Physics and you keep me as the referee. And that paper was appreciated and accepted. And I got a personal note from him. So, a tall giant of a scientist, amazingly clear in his thoughts, and also significant contributions to the very basic aspect called uncertainty relation, which has been with us since Heisenberg. So you'll be amazed to see many of those things are now finding experimental verification. There was a talk, if some of you are curious, by Sponar, which is there in the YouTube. You will find out that how many aspects, influence uncertainty in a given measurement. So I think we'll stop here. Alok, if he comes, we can talk about all this later. Now, Slava has joined. Professor Spiridonov, are you around?
Hello, Prasanta. I'm here.
So I know
nice to see you.
Yes.
So you hear me and see me. That's very nice.
Yes.
Okay.
Yes. Now, Professor Avinash Khare will formally introduce you before you start your talk.
Okay.
It is my great pleasure to introduce today's speaker, Professor Spiridonov. We popularly call him a Slava. I was very lucky to meet Slava in Montreal a long time ago, 25 years ago almost. And we had some overlap of work about para-supersymmetry in quantum mechanics, and also then about self-similar potentials in quantum mechanics. We had nice discussions, and he's a very reputed mathematical physicist, and now actually more tending toward mathematics than physics. So we have right now, but he has done very outstanding piece of work, and it's very nice of him that he agreed to give today's talk. So I request Slava to give his talk. Thank you.
Okay, thank you very much, Avinash. So it's a great pleasure to give a talk at your school. It looks so great, so big, that I really wonder how you will manage to tackle all that things continuously. So big success in a sense. And especially I would like to greet my friend Professor Panigrahi, Prasanta, with whom we were postdocs in Montreal. It's frightening to say 30 years ago. It was great time and great pleasure to stay in Montreal, and so I have very nice memories about that time. Okay, so today I would like to talk about the things which I was doing actually during those times, not the things which I was doing over the last 20 years. As Avinash mentioned, I turned more to mathematical issues. I will say a little bit, but not, of course, in detail, because this is a conference on school on physics. But you will see what it will be all about. Let me share my screen. I hope it will work. So this one probably, yes. Do you see it?
Yes.
Let me then put this back.
Yes, fine, Slava. Go ahead.
Okay, let me start. So I want to talk about the some quantum mechanical things, but as Prasanta told me, this week has general title physics, symmetries in physics. And so I decided to give some short introduction about some philosophy about what I think about physics and symmetry. And this is my abstract, which I sent last week. And first, I wanted to say about non-relativistic quantum mechanics and in particular factorization method which was developed in that in quantum mechanics. But and then talk about coherent states. But during the preparation, I changed the schedule, and I decided first to talk about coherent states. So be ready to that. Okay, what about physics and symmetries? The general claim is that symmetries govern the world in the most fundamental meaning of these words, because most of fundamental physics research is devoted to search of symmetries inside these physics theories, and then trying to break them in various ways, and that so have some experimental consequences for having symmetries and breaking them. And mathematically, of course, symmetries mean the group theory. So well-known mathematical subject, which is hidden in these physical theories. It's discrete or continuous group theory inside these models. And of course, algebras, in particular Lie algebras, which govern the continuous symmetry groups. And top symmetry groups are present in the quantum field theory and in string theory. So very fundamental theories which were developed for over the decades. In particular, elementary particles, which we know, they are irreducible representations of Lie groups living in the Hilbert space. Namely, the Lie group, which is definitely supported by reality, is Poincare group times some gauge groups, some flavor groups. And of course, many, many discrete symmetries like parities, charge conjugation, baryon symmetry, baryon number preserved symmetry, and so on. And the standard model lives in rather cute you see, I decided to give this group to you, to show that it looks rather bizarre to me. You see, Lorentz group times translation group. This is Poincare group. This is standard model. Gauge group, you want cross SU2, cross SU3. It's some flavor group, which of course has similar structure. It has, as I said, electric charge conservation, symmetry, U1, then baryon number, some isospins, and so on. So this long chain of letters shows that there is, of course, a lot of symmetries on the one hand. On the other hand, it's not satisfactory that it is so broken, as if big stone was been broken into small pieces. So, but that's exactly the search of fundamental physics to understand these things. And of course, some more complicated hypothetical conformal and supersymmetric extensions and so on and so forth. And another theorem behind these continuous symmetries is the conservation laws of the nature and so on. Of course, this is very vast subject, and I would like to squeeze it to one-dimensional quantum mechanics and show how algebras and Lie groups work in the one-dimensional quantum mechanics and how they help to tackle so-called solvable cases of Schrödinger equation. And as an introduction to this subject, I will start from the simplest exactly solvable case, which of course all of you know perfectly well. But let me do this introduction. It's a school. So the Hamiltonian of harmonic oscillator in this canonical normalization, when Planck's constant, frequency and mass of the harmonic oscillator particle is set to 1, and then this Hamiltonian takes, it's just a p square plus x square over 2. This is momentum, this is the coordinate. And quantum mechanics means that we quantize these objects, these are operators, and the commutator of them is equal to I, where I is the imaginary unit. And the textbook standard factorization of this Hamiltonian is the following one. It is represented as a product of two operators, A plus times A plus some 1/2, where A plus is this combination of momentum and coordinate, and A is this combination. And it's very easy to see that if you substitute these operators here, then due to this commutation relation, exactly this 1/2 is killed, and you get this quadratic form. And this is these three operators form the simplest Lie algebra. namely the Heisenberg algebra, with the following commutation relations. So A dagger commutation equal to 1, and Hamiltonian commutes with A with minus sign, and Hamiltonian with A plus with plus sign. So standard things. Ground state, or the vacuum, is defined as a zero mode of the annihilation operator A. So it kills the vacuum, and it is assumed that vacuum is normalized, of course, to 1. And the complete set of eigenfunctions of the system is built by a raising operator. But you take a raising operator, act on the vacuum sequentially, and you get excited states. And the energy of these excited states is n plus 1/2, where n is integer 0, 1, 2, and so on. And this is the standard eigenvalue problem. So well-known harmonic oscillator quantization. And the action of the raising and lowering operators is also very easy to find because of the normalization. You have the square root of n plus 1 for raising and square root of n for lowering operator actions. And of course, for n equal to 0, this is 0, and as it should be for the definition of the vacuum. Very simple, very nice. Let's go to the next slide. Another set of simple facts, known facts. But from the next slide, something new will start. So in the coordinate representation, when the momentum is just a derivative up to the product, up to this minus I multiplier, and the Hamiltonian becomes differential operator of the second order, and then the eigenvalue problem unfortunately, I cannot, for some unknown reasons, it cannot highlight. I only with the mouse can show where I am pointing out. I hope you can see it. So you solve this differential equation of the second order. And with that, it's easy to solve in both, well, let's say mathematically easy to solve. And the answer is the following. So wave functions are given by exponential of minus x squared over 2 times some polynomial. And this polynomial has very nice definition. It's just an action of differential operators on the exponential of x squared. And it's called Hermite polynomials. And this constant here is just a normalization, which it started to highlight. Very nice. So very well known orthogonal polynomials and very well known solutions, very well physics understood behind these formulas. So let me go to coherent states. What are coherent states? These are special wave functions, which are eigenstates of the lowering operator A. Actually, there are 3 definitions of coherent states. One is this one about the eigen solutions of the eigenfunctions of the annihilation operator. Another definition, which is not unique, but still useful, the fact that this state, coherent state, is the one which minimizes the uncertainty relation. The product of delta x, delta p is equal to 1/2. And group theoretical third definition is the following. It refers to the Heisenberg group elements. If you take exponentials of these generators of this Lie algebra, Heisenberg algebra, with arbitrary parameters, then you get group element. It's well known in the theory of the Lie groups. And if you act by this operator, which is called displacement operator on the vacuum, then you get exactly the same state. So more or less, all 3 definitions give one and the same state. And by expanding this into or using Baker-Hausdorff formula, you can simplify this operator, split into the product of 2 operators, and then easily check that, easily find that it's given by the following sum of eigenfunctions of the Hamiltonian and eigenstates. And explicitly, it's very simple object. It's just exponential. So you have exponential of quadratic form of alpha and x, and it's essentially the Gaussian. So that's the coherent state of the harmonic oscillator. All this is well known to you, and so I was describing this just to indicate that even in such simple systems as harmonic oscillator, there's still some room to do some new things. And here are the things which I have done in those times in 1994, and last year I had some chance to complete what I was doing this 20 years ago about coherent states of the harmonic oscillator. And it goes as follows. So the factorization of the Hamiltonian, which I used in this picture, which everybody uses in this picture, is actually a highly non-unique operation. Namely, the same Hamiltonian can be factorized in the product of different operators. Namely, A, now capital A plus, is again this small a plus times some operator U. And capital A annihilation operator is now some operator V times old A small annihilation operator. So I introduce from the right and from the left some operators. And in order for this operator to be the same as before, the p square plus x square, you must have this nice simple result. U times V must be 1. If we demand, and in this picture it's exactly the case, that A plus is actually the Hermitian conjugate of A, so dagger is equal to A dagger is equal to A plus, then U must be V dagger. And it means that essentially that U is a unitary operator. So U must be unitary. Its dagger is equal to inverse of U. Then, now it's one restriction. And another restriction which you have to impose is the following one. Let's demand that these new operators A and A plus satisfy the same Heisenberg algebra as before. The commutator of A and dagger, or A plus, equals to 1, which would mean that we have actually the canonical transformation, which is very useful both in classical and quantum mechanics. What is the condition for the validity of this demand? It's very simple. Since this is p square plus x square, then when you multiply in inverse order A plus, you see that you have actually this condition, that U dagger p square plus x square U equals to p square x plus x square, which means that this operator doesn't change the Hamiltonian. It's some kind of unitary transformation on the Hamiltonian, preserving the Hamiltonian. And let's play with this idea. And I will give you two simple operators of U, explicit, very explicit forms of the operator U, which satisfy this condition, of course, and which have certain consequences. The simplest one, which I have found from some ideology in 1994, is the parity. P anti-commutes with X and with P capital P anti-commutes with X and with P. And it's square equal to 1. So both pieces are preserved independently, P square and X square. Another possibility consists in choosing as this operator U the Fourier transformation or its inverse. So Fourier transformation is defined in the following way. It's integral over full real axis of the function which you want to transform multiplied by the exponential. Very well-known thing. And this is the normalization which gives you a nice property in the sequential action of this Fourier transformation. And the inverse is obtained just by changing the sign in the exponential, essentially complex conjugation. And so this times this equals to 1, standard thing. But if you twice apply a Fourier transformation as it is written here, then you will get the parity operator. Change of the function from f of x to go to f of minus x. So Fourier transformation is nothing else than the square root of p, of parity. And its inverse, of course, 2 is the, as you know, the square roots have the double values. So in this case, it's inverse Fourier and Fourier. And the first power of the Fourier transformation is 1. It's fundamentally important mathematical transformation with many, many very nice physical consequences and usefulness. So this F, Fourier transformation, what it does with P and X, it makes symplectic reflections, which preserve the canonical commutation relations, namely fx f minus 1 is p, but fp f minus 1 is minus x. And the inverse operator acts in the opposite way, so it changes the signs of different position of signs, minus p and x. So now I will discuss what happens with these two choices, with these two options, when u is chosen as p and when u is chosen as Fourier or its inverse. What we can do with that? Because as I said, it's canonical transformation. This non-standard approach to Heisenberg algebra allows us to define non-standard coherent states. Namely, as I said, coherent states are defined as eigenfunctions of the lowering operator. But in this case, it's the same. So A small or A capital, both are lowering operators. A full picture, which I described before, is valid for A capital, A plus 2. So let's work with A capital. So eigenfunctions of A capital is the same as if I demand that A small, this canonical lowering operator, acts on the state and it rotates it additionally. So it's not an exact eigenfunction, but some old eigenvalue U alpha times action of the operator U. So if U is the parity operator, it's quite easy to solve this equation, to find this explicitly this form of this coherent state. And it is given by the following superposition of canonical coherent states, which is, since both states, this one and this one, are macroscopic quantum mechanical states, and you have superposition of them, then essentially this is the Schrödinger cat state. And that's exactly what I was doing long ago. And I will indicate how I came up to such a construction from the factorization method. It's a little later. And in the coordinate representation, it's easy to find that this superposition is given by the following explicit form. Again, it's exponential of some quadratic form times cosine of linear function of x. And the point is that this coherent state is extremely popular in quantum optics. Namely, in 1986, Jurk and Stoller, in an ad hoc manner, suggested to construct exactly this state, this superposition, and to detect it in optical experiments in media with some specific properties, and discussed various experimental implementations of this state. And so their paper, which I guess it's here, just a second, I was saying it for showing. Here it is, yes. This one in Physical Review Letters by now has obtained almost 1,500 citations. And so people discuss in very different ways how the states work in quantum optics, what one can do with that, and so on. So it was essentially what appeared that I gave a group theoretical interpretation of the Jurk-Stoller coherent states. But now, last year, I got a chance to continue this research. You see, it took quite a lot of time, 27 years. So now I'm choosing for this operator U, the Fourier transformation. What then kind of equation we get? So action of the standard annihilation operator on state is equal to alpha times action of the Fourier transformation. So now we have integral differential equation, or equations, because for Fourier and inverse Fourier it's different. It gives different solutions. And here I should remind, what are the eigenfunctions of your Fourier transformation? That's what is necessary technically to solve this equation. And the very nice property of the harmonic oscillator system is that eigenfunctions of the Hamiltonian are simultaneously the eigenfunctions of the Fourier transformation. Namely, action of the Fourier transformation on the eigenstate or energy eigenstate has the eigenvalues epsilon n, I in the power n. So I in the fourth power is 1. So you split your spectrum of the harmonic oscillators into 4 sectors. And those 4 sectors you can use for building some, to construct the coherent states of search of these ones associated with Fourier transformation as superpositions of the canonical coherent states. So here is the final answer. All you should do, you should expand this function or this abstract function in terms of the eigenfunctions of the Hamiltonian and compute the coefficients which appear from this demand, because this is all those Hamiltonian eigenstates, they are simultaneously eigenstates of the Fourier transformation, so you diagonalize this problem. And here is the final answer. You have superposition of 4 now coherent states with very nice choice of the phase factors. So you multiply alpha by eighth root of unity of this form. Then you use the so essentially you play with the eighth root of unity, and the combination is now of this form. So I like this very much when I have found it last year. The form, and in the coordinate representation, it has the following form. Again, some exponential quadratic form times some cosh function plus some sinh function. So it looks now more complicated, but still, of course, it's a combination of exponentials, nothing else. This is for Fourier. What about the inverse Fourier? Inverse Fourier is obtained simply by changing signs in these phase factors, minus here, 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 and here. And you will get the inverse Fourier transformation coherent state. And here I would like to pose the question about the to optic experimentalists or whatever people working in optics. Is it possible to find for this coherent state similar meaning and experimental appearances as for the Jurke-Stoller state, because it's not too far complicated from the Jurke-Stoller state, but and has an actual nice form. So I guess that it looks beautiful actually, and everything beautiful should appear somewhere in the nature. That's Dirac's thesis. So I expect that this also should be useful in some of the experiments. I myself, I'm a theoretician, so my job is to propose such things, and maybe someone will be interested in to investigate these states from this point of view. Okay, now general case. Namely, now I choose as the operator U, the general operator which rotates coordinate momenta. And this is a well-known thing. This is nothing else than some time, artificial time evolution of the coordinate and momenta of the quantum harmonic oscillator, and solution is also known. So you have to solve the now non-stationary Schrödinger equation, and the solution is just exponential of the Hamiltonian, but you have to choose instead of real-time t, the artificial parameter phi, which is entering these rotations. In terms of the creation and annihilation operators, it's very easy to do. Then the evolution is computed very easily. So it's just a simple exercise in differentiation the operator product of operators. And it's easy to see that evolution is given by exponential for both annihilation and creation operators with different signs. And if you now substitute these formulas into the definition of canonical coordinates, you will get exactly these formulas. So it's a proof of the fact that this operator is performing this change. And now I come to the most general form of this integral differential equation, namely action of the annihilation operator on some coherent states. Now, coherent state depending now on this additional parameter phi, continuous parameter, is given by the action of this evolution operator on the same state. I forgot here the at alpha. It's missing here. There must be some alpha, which appears on the right-hand side on the next part of the formula. So, and it has the following form. Its integral operator is some kernel k acting on the wave function psi, and the kernel actually is very old. It's called Mechler kernel. It's actually the green function or propagator for the harmonic oscillator, and it's an analytic continuation of the Mechler kernel. He has found it for the hit operator, and just you do rotation to the imaginary axis in time, and you will get this form of kernel. And it's easy to see that for phi plus minus pi over 2, it reduces, falls down to the Fourier transformation. And now the normalizable solution of this integral differential equation is given by the superposition of Hamiltonian eigenstates with additional phase parameter. But now you cannot represent it in general as a superposition of finite number of coherent states. So it's not kind of a cat state. It's called the Titulayer-Glauber state, some example of the Titulayer-Glauber coherent state. So it's some more general. So I would expect that that Fourier type of coherent state is more interesting from the point of view of investigating whether there are some applications or not. Okay, now I turn to the general subject. That was all I wanted to say about the harmonic oscillator. And as I said, the last two results, they are new. And that's exactly the reason why I decided to give it first, to present new results. Now I will pass to the survey, some review of the things about factorization method and description how from that method you can obtain the solvable potential, a very rich class of solvable potentials. It goes as follows. So first I remove this multiplier 1/2 from the normalizational Hamiltonian and use the following form. So minus second derivative of x plus sum of function u potential. Let us take arbitrary potential u of x, completely arbitrary in a sense. Well, for which there is meaning for this Schrödinger equation, and construct a chain or infinite chain of Hamiltonians which are related to each other in a very particular way. Namely, now index j is just an integer, any integer, positive or negative, it doesn't matter. And I want to consider the chain of eigenvalue problems, infinite chain, in which neighboring members of this chain, of these Hamiltonians, are connected to each other through the action of the first order differential operators. So the wave functions of the j plus first Schrödinger equation is obtained from the wave function of the Schrödinger equation with the number j after the action of this operator capital AJ, which is the first derivative plus some function. So that's essentially what is called Darboux transformation. And what we have now actually discrete time evolution of the Schrödinger operators, and this equation together, they form what is called in the theory of integrable systems the Lax pair. And this Lax pair was constructed by Infield in 1941. And of course, there must be some compatibility condition, and it's easily found. Namely, you act by Hamiltonian Lj plus 1 onto its eigenfunction, which is defined here. And it should have the same eigenvalue as for the whole chain. You see, lambda is everywhere the same. And you replace now this piece of the equation by the action of Lg times psi j and hide lambda inside now this thing. Now you get this intertwining relation, very easy. And this is the equality of differential operators of the third order. You substitute this expression and these expressions into this operator equation, equate coefficients in front of derivatives, and here is the solution. So potential of the j plus first Hamiltonian is uj's, potential of the Hamiltonian uj plus 2 f prime. F prime means derivative with respect to x. Then some condition for another derivative, and you resolve this vanishing of the coefficients in front of another derivative, and resolve all that, and you find that uj is fj square minus fj prime plus some constant. This is integration constant, which appears from integration of this equation. And function uj plus 1 is fj plus fj prime instead of minus with the same constant. That's it. You resolve the condition of compatibility, and your system now is consistent. What you have obtained? Actually, you have obtained the factorization of the Hamiltonians, and it goes as follows. You can check that if you consider formal conjugate of AJ, which just changes the sign in front of the derivative, then Lj is equal to this expression, A plus lambda j. And the j plus first Hamiltonian is obtained just by permutation of aj and aj plus. And it is, of course, again, by definition, aj plus 1 plus times aj plus 1 plus some constant lambda j plus 1. Because you see, you just shift j by j plus 1 here and use it here, but you have the permutation of the operator factors. And these two formulas are consequences of the resolution of the compatibility condition. And of course, you have now a second defining relation for the now this formal conjugate of A plus. If it is real conjugate, Hermitian conjugate of A under certain constraints, it's true. Then your Hamiltonians are Hermitian operators, and you're fine. And if you now substitute into this operator chain the expressions for the operators A and A plus, then you will have the following functional equation, So non-linear, you see fj plus 1 square, fj square. Differential is here and here, and some constants, integration constants. This is exactly the factorization chain was formulated by Infeld in 1941. 1 year before, Schrödinger has suggested the method called factorization method to solve his equation. And the Infeld formalized it in this way, and so the factorization method was actually formulated by Schrödinger and Infeld. And it works as follows. If you demand that the vacua of this LJ Hamiltonian, eigen zero modes of the operators AJ, if they have, of course, now this explicit expression, if they are normalizable, then this is really, truly the vacua of the corresponding Hamiltonian. And if all of them, which you choose in this chain of Hamiltonians, if for all these members of this chain of Hamiltonians, these functions are normalizable, then you get step by step the eigenvalues and eigenfunctions of the Hamiltonian, of the initial Hamiltonian. So the vacuum is obtained by this integration constant. So only for very special choice of the integration constant, this state will be normalizable, and that's exactly the way you determine the vacuum energy. And then you use the generalized phrasing operator, action of the A plus operator in this vacuum state. You see, J number is here, but a vacuum state of the higher member. You act, you obtain the wave function, which is the eigenfunction of the previous Hamiltonian. So in this case, lambda j plus 1 is the second eigenvalue of the Hamiltonian Lj, and Lj was the vacuum. And so on. You're repeating this steps by step, you can reproduce the full discrete spectrum energy states, and so that's exactly the essence of the factorization method. Of course, there are very nice, very strict conditions for this to work, but that's the technique. It's normalizability of the wave functions, positivity, hermicity, and so on. I will not touch these things here, just indicate how it works. Now I jump to formal things, namely to I will describe you the special family of of solvable potentials for which you can say something about spectrum and eigenfunctions. For that, I will need this n-step evolution operator. So sequential action of these operators, n in the product, and its conjugation, its opposite product from j to j plus 1, j plus 1. So these two operators, m and m plus, they satisfy these intertwining relations. So essentially, they look similar to what you saw already. It's just now, instead of a shift of the time, discrete time by 1, you shift it by n. And what is important is the following fact, that the product m plus m is the product of the Hamiltonian J with these eigenfunctions, eigenvalues lambda j plus k. So it's essentially polynomial of the nth order with particular zeros. And the inverse product m plus also is the same polynomial of lj plus n. It's different now, Hamiltonian in the chain, with, of course, slightly different constants lambda j zeros. And the connection between wave functions is also now easy to see. So eigenfunctions of the Hamiltonians with the number j plus n is just the action of the operator m on the eigenfunctions of the Hamiltonian with the number j. And in this way, you construct the full discrete spectrum along this factorization method. That's general. Until now, I did not restrict any Hamiltonian, any potential. Now, the question is about where are the exactly solvable cases, which we like very much and study in the university course on quantum mechanics. So Schrödinger has found first examples in an iterative manner And Infeld, as I said, gave some mathematical background in Lux-pair formulation, chain formulation, and essentially he posed the problem as the problem for solving this equation, nonlinear differential difference equation. And mu j, I denoted the difference of these sequential numbers, lambda j plus 1 minus lambda j. So that's what is new. You see, when you were factorizing and permuting the operator factors, you did not introduce any new variables. And Infeld said, you have to introduce some discrete time, in my terminology, which can be considered as a continuous variable. And so essentially you introduce a new degree of freedom into your formalism. And then he said, as this should be considered as, let j be complex variable, not some discrete variable, but complex. And then we can try to solve this equation, look for analytical functions of fj of x, which are analytical both in x and in j. And so he and later jointly with his student Hall, they classified the solutions which have finite Laurent expansion in this complex variable j. So it appeared that this expansion in j has a finite number of terms only for this ansatz, which is the ansatz of generalized separation of variables. It's called also similarity ansatz. And they declassified all solutions of this ansatz and have found that spectra can be either Coulomb type 1 or j square harmonic oscillator or some Morse potential oscillator, Morse potential spectra. So that's the set of solutions that they have found in this way. I will describe you the different family of solutions of this factorization chain, which follow from the different type of symmetries than these ones. These symmetries of this ansatz I will not discuss. There are very simple symmetries of this chain. Namely, if you found the solutions which with the number fj and lambda j, then if you shift j by some integer n, it doesn't change. It maps solutions onto solutions. Fj is a solution, fj plus n also solution of this infinite chain because it's homogeneous in j. There is no explicit dependence on j. So this is a symmetry, discrete time shifts. Another very simple symmetry is the similarity summation associated with the affine transformations of the coordinate. If you replace coordinate x by qx plus a, some constants q and a, then essentially you do a affine transformation of your system, and of course it's a very simple symmetry transformation. And it's not difficult to see that if j of x is symmetry with mu j, then q fj with the shifted argument and mu j multiplied mu square is also the symmetry of this chain. So very trivial symmetries. But the idea how to join them and to fuse and to apply as a symmetry reduction is very rich. Namely, I define the self-similar potentials as those potentials which for which these two symmetries are equivalent. So essentially, this is an invariant solution under this, but these two symmetry under the combination of these two trivial symmetries. So if I demand in this chain that shift of the discrete time is equivalent to affine transformation of the function, here should be j. I missed the j number here. And the similar thing is here, that mu j plus n is multiplied by square. I close my chain. Before it was completely infinite. Now you see, after n steps, I return back to the same system with affine transformation. That's a very simple idea. But the result is very important and very interesting. First, it is possible to solve this constraint on the spectra. So you see, this now becomes the constraint on the type of spectra which are admitted for these systems. You solve that, and you will find that now the spectra, discrete spectra essentially, have the form of finite number up to n geometric progressions. So if they exist, the systems with such symmetry, then they must have discrete spectrum which consist of a superposition of n geometric progressions with the increment q square. Since for non-relativistic quantum mechanics spectrum cannot grow faster than n square, then this q parameter must be chosen as smaller than 1. And in this case, these geometric progressions, they accumulate, lambdas are negative, and they accumulate near the 0 point from below. And above the below zero energy, you have the continuous spectrum. That's the physics picture behind possible physics picture behind these systems, and they are somehow confirmed in some ways. And that's first simple physical consequence of this very simple construction on this factorization chain, which are imposed from the symmetry reduction principle. Now, from the algebraic point of view, we come to the quite popular and rich algebraic structures, which are called quantum algebras. And they express this operator set familiarity, which I defined in the functional way. So namely, remember that algebra, which, not algebra, but a relation which I was describing before, when the product of m plus times m was giving a Hamiltonian polynomial of the Hamiltonian Lj, and inverse m times m plus was giving a polynomial of the Hamiltonian Lj plus n. And now I impose the constraint, that's exactly the same closure, that this Hamiltonian with the number j plus n is equal to Hamiltonian Lj up to the affine transformation, namely multiplication, action of some operator u, which I did not define, but actually in this context of these self-similar potentials, it is the operator of affine transformations of the coordinate x, and plus some constant. If I impose this constraint, I close my algebra in a sense. And if I denote now L naught, B this U minus 1 times M naught, B plus as M naught plus times U, this is essentially almost the same as in the harmonic oscillator case, which I described you, that there is the freedom on with the choice of the freedom in the factorization, choice of the factorization operators. That's exactly what appears here. Then these three operators, L, B, and B plus, satisfy this polynomial quantum algebra. LB plus equals Q squared B plus L. This is inverse. So if you conjugate this, you get this, or if you conjugate this, you get this. And the product of BB plus is polynomial of L with the zeros of this type, and BB plus is polynomial of Q squared L with the same zeros. That's it. This is the quantum algebra you get. And if you choose n equal 1, you have linear operators on the right-hand side. And that's what is called the Q harmonic oscillator algebra. A dagger minus Q squared A dagger A equals to 1. And A differs from B just by normalization by a constant. Lambda is negative, Q squared is less than 1, so this is positive. And if you choose the Hamiltonian of this form, H, A plus A minus this constant, it's a special constant, then you get exactly it's just consequence of this algebra. Then this operator must have it may have as a discrete spectrum the one geometric progression, Q in the power J divided by Q squared minus 1. So this was a rather general definition of these self-similar potentials, but it is very, very rich. In special cases goes as follows. Let's kill Q, no any Q, 1. Let's kill mu, also the constant which was appearing in this ansatz of the closure, operator closure. You see it was here. So Q equals 1, U is equal 1, mu is 0. So what you have, Lj plus n equals to Lj, which means that in your system, you have nth order differential operator, which commutes with the Hamiltonian. And so this is the condition of commutation. And this is well-known system. This is called finite gap potentials. The potentials of one-dimensional quantum mechanics, which may have finite number of admitted zones inside your spectra. So no discrete spectrum, only continuous, but it appears in the form of the band structure. And the number of these bands is finite. And it, of course, number of bands depends on this integer parameter n, the order of these operators B and B plus. So all finite gap potentials emerge in this way in the one-dimensional quantum mechanics. Very nice result, because finite gap potentials are very important in quantum mechanics. But if you choose everything the same, except that you choose as u the shift operator, it's allowed in this construction, then you will get commutativity. Yes, but now B and B plus will be not differential operators, but differential difference operators. And that's it. You essentially lose a lot of things. And I was able only in the case of n equal 1 to find the solution of this equation. Now you will get the differential difference equations, which are very complicated objects, but in the n equal 1 case, it leads to the elliptic potential, and Weierstrass functions gives you some solution. But as soon as you take n bigger than 1, I don't know anything about what kind of functions emerge there, and so it's completely open. What kind of deformation of finite gap potentials one gets. You see, in this case, elliptic potentials were showing only for n equal 3, when B and B plus were differential operators of the third order. And in this case, already for n equal 1, there is the elliptic potential. So this phenomenon until now is not well understood, both from mathematical point of view, essentially. But it goes more and more complicated. So if you choose as q equals 2 plus minus 1, which means that u is q square is 1. U is either unit operator or parity operator. Then you can reduce, you have the algebra, which is now polynomial algebra again, but now it's more not Q, but standard Lie type algebra. So commutator LB plus is plus B, and LB is minus B. And the commutator of B plus B is some polynomial of the n minus first order of the Hamiltonian L. And the potentials which define these systems are also very, very complicated. If n is, for n equal 1, it is the harmonic oscillator in both cases, for 1 and p. So it's the only case essentially which has elementary function solutions. As soon as, well, n equal 2 also has elementary function solutions. But as soon as n bigger than 2, then you get so-called pan-level transcendence as the potential, as the functions defining the potentials. And that's very complicated set of very nice special functions. Well, I will not say more, just say that these pan-level transcendents are being investigated thoroughly for over 100 years, and quite a lot of things are known about them. But still, it is highly non-trivial, highly complicated, and non-explicit. And so, but at least it gives the terminology. So for general case, when U is the scaling operator by Q, that's the general case for the, well, here I removed the constant, addition constant, Qx plus A it was, but just Qx. Then you can say that these general self-similar potentials are described by some Q-deformed pan-level transcendents and the high-order analogs. Well, another very nice case, when Q is the root of unity, then this power of U in the m's power of U is 1. It means that m's power of B and B plus commute with L. You get special finite gap potentials. There is some crystallography and the quasi-crystallography hidden in these systems. Namely, for small values of M, you get elliptic potentials with hexagonal and quadratic and square lattice symmetries of the lattice of periods. So crystallographic systems. For M bigger than 3, for n equal 5, for instance, I expect that there is the Penrose tiling which emerges in these systems, and these special finite gap potentials are defined on the Penrose tiling. But it's open problem to show that exactly the case when m is equal to 5. So these nice systems of special finite gap potentials still not investigated in full scale. And very, very trivial situation with very, very non-trivial algebra. If you choose fj with minus lambda j, then you will see that your potentials, you have the solution of your equations when the potentials are equal to 0. And all Lj Hamiltonians are just minus second derivatives. 0 potentials. So it's free particle. However, full algebra is there. And for n equal 1, it is the Q oscillator algebra. So essentially, we have a realization of quantum algebra on the eigenfunctions of the free particle, which are exponentials. I will say a little bit more later about this. Okay, coherent states again. Now about the coherent states of these self-similar potentials. They are, of course, much more complicated than the coherent states of the harmonic oscillator. I will say only briefly what are they structurally. So if energy value is less than 0, then for this part of the spectrum, the lowering operator is B. You look for the eigenfunctions of the operator B. And they are obtained as the action of so-called Q hypergeometric function of this type with the operator argument, where argument is proportional to B plus, acting on the first n eigenfunctions of the Hamiltonian. So essentially you have n, the set of n coherent states of that type, which are obtained in this way. For n equal 1, this is Q analog of the exponential function. You see, for the harmonic oscillator, you essentially have exponential of operator argument acting on the vacuum. It's analog of that, but with more complicated function than the exponential, Q exponential in the simplest case. But it's the same picture, more or less. But for lambda bigger than 0, for positive energy states, the lowering operator is now not B, but B plus. You see, in this algebra, you have both operators B and B plus may work as lowering operators and raising operators. It depends on the part of the spectrum. Very unusual situation. So you can define now coherent states as the eigenfunctions of the B plus operator. And there are such operators, and there are such coherent states. And instead of now this function, you have so-called bilateral basic hypergeometric series, or in the case of continuous spectrum, you have Ramanujan integrals. So Ramanujan integrals, they are normalizations of the special coherent states appearing in this picture for particular case of the self-similar potentials. Very nice output of famous Indian mathematician Ramanujan, which I hope is pleasing you to hear. Okay, now how it works in the case of this free particle system. So let's take free particle Hamiltonian and factorize it in the following way. A plus times A, where A plus is minus derivative plus constant times the scaling operator, and A is just scaling operator inverse times derivative plus constant. So you see differential operator times with constant coefficient times scaling operator, and it's conjugate. So if you substitute this here, you will get exactly the second order derivative. That's it. Now, there is no discrete spectrum. Therefore, this type of coherent states do not exist for this system. However, this type of coherent states do exist. If you look for the eigenfunctions for this A plus operator, which is now becomes the differential Q delay, Q difference equation. Then there are solutions of this equation which are normalizable. They lie in L2R. So it's a normalizable, discrete, the real physical states. This equation is very cute. It's called advanced pantograph equation, differential, Q difference. And it governs, for instance, the flow of currents in trolleybus, tramway, or some railroads with electric circuits. Also, it appears in different other places. And here it emerges as the equation which determines some coherent states of the free particle. And of course, the question is, what are the properties of these coherent states? I don't know. I just formulated them and did not investigate at all how they look numerically, for instance. Okay, I have not that much time left. Therefore, I will wrap up two more sections which are left. Just giving some hints what else can be done on the background of this solvable cases of the Schrödinger equation and in the general formalism of factorization method. First is, of course, the relation to classical integrable systems of Korteweg-de Vries equation type. Namely, let's take our chain of Hamiltonians with the potential uj, and at some time t. This is not time in the Schrödinger equation sense, but some real time in the classical physics sense. And demand that now our evolution of these wave functions or solutions of the Schrödinger equation develop in time according to this law. So partial derivative with respect to time is equivalent to the action of the third order differential operator depending on this u in this cute way. Then you look for compatibility of the Schrödinger equation with this time evolution equation, and you see that these coefficients, your potentials, must satisfy Korteweg-de Vries equation, which is the third order differential equation, partial differential equation, and nonlinear. And all those functions, FJs, superpotentials, which we were describing, constructing, they giving some particular solutions of this equation now. And in particular, they are related to solitons of this equation. It's not qubit, but soliton running in the optical cables, which now transfers the information. So it's not quantum, but classical signal transmission. Okay, so very simple. If you substitute these ansatz for fj's of this form, so derivative of x of some function phi naught, then you will see that phi naught must satisfy the same Schrödinger equation as before with this exactly this special eigenvalue lambda j. And so eigenfunction of the next Hamiltonian is obtained. This is just the Darboux transformation, factorization, action of a j is obtained as a combination of two Wronskians. This Wronskian divided, this is also Wronskian of one function. So you see it's combination of some especially chosen test function phi naught and of the function psi, which you were taking as a solution of one of your Schrödinger equations. And this formula can be repeated iteratively and result in the following fact. After the n steps of this factorization and refactorization along the factorization chain, you obtain the potential, which differs from the previous one, from the index j, just by the second derivative, logarithmic derivative of the Wronskian of the some set of test functions of eigenfunctions of the previous of the LJ Hamiltonian, these ones, with the eigenvalues lambda j plus k. So you take this equation, solve it, take test functions phi naught, solving this equation, perform this discrete time evolution, and then the potential obtained in this way has this explicit form, where W is the Wronskian. The same similar formula for the wave functions. You see this is M operator acting on the MJ gives you a ratio to Wronskian. So this is an explicit realization, analytical in a sense, realization of this operator action. And if you choose the initial test eigenvalue problem, this one as the free eigenvalue problem, namely LJ is just free second order derivative, so free particle. Then solutions, test solutions are exponentials. So you can choose them in the following way as a cosh of some particular combination of these variables with some constants kj, this in some shift, some constants theta naught. So three constants kj determine the energy, kj cubed determine determines coefficient the time evolution, and this is just some initial phases of these functions. So if you choose these functions, then what you get, this resulting potential, this uj, if uj set to 0, then un is the reflection potential, which is n-soliton solution of the Cartlet-de Vries equation, for which kj square is the amplitude and speeds of the solitons, and these theta j's are phases of solitons. So essentially, solutions of the free Schrödinger equation allow you to build the soliton solutions of the complicated Cartlet-de Vries equation. Now, okay, I will say a little bit more in words. This particular set of functions, which I described you here with this Cauchy and Sinch function, so UJN, also emerges in the self-similar potentials. I forgot to say that, and only now realize that I forgot to say it. When I was mentioning special cases, there is one more special case which I missed, namely Q equal to 0. When I choose Q equal to 0, essentially I multiply F by Q, which is 0. So essentially I kill one of the final Q. So I interrupt my chain by saying that after n steps, I should get 0 potential. And this is exactly the case of the solitons. So these solutions, this solution of the Schrödinger equation and of the Cartlet-de Vries equation is sitting inside the self-similar potentials for the choice of Q equal to 0. And n, the period of closure, is exactly the number of solitons. And now you can construct, using these things, the actual self-similar potentials in the following way. You keep reproducing your solitons with energy parameters multiplied by Q square. So essentially, you need to build, I don't want to go into detail, just to give you a hint. If you take infinite soliton potential. Actually, using this technique, you can construct, as is this well known, the potential with the prescribed energy spectrum. So you essentially, you take now this self-similar spectrum, which is a superposition of geometric progressions, as the spectrum of the infinite soliton potential. So essentially, you continue this procedure in building the soliton solutions up to infinity, but you choose these coefficients kj in a very special way, namely kj plus n must be q kj. And similar, then this here it will be the same, and this constant should be just periodic. Altogether, this will give you infinite soliton potential. We're reproducing the spectrum of that self-similar potentials. Okay, that's more or less all I wanted to say, except that there is another nice interpretation of these potentials I was saying, and of the whole formalism. Namely, it gives you, it allows you to generate Ising chains and the lattice Coulomb gases, both one-dimensional and two-dimensional. So sorry, I'm not able to say about anything about that right now. Let me complete it. My talk, let me finish my talk. So solvable potentials, which I described you, they emerge in this picture as the symmetry reductions of the infinite chain of symmetry transformations of the Schrödinger equation. And the whole formalism is, of course, related to, it's called factorization method of Darboux transformations. Some people call it supersymmetric quantum mechanics methods. Is related also on top of, behind that, you can construct coherent states, nice set of coherent states, solitonic solutions, some Ising chain and 2D Coulomb gases, which I skipped. And for me, what I was doing over the last 20 years is actually I was working on the mathematics or behind such type of systems, not on at the level of Schrödinger equation, but at the level of second order difference equation, where you have completely different set of factorization methods. Even the factorization actually disappears. It's more complicated. But you have nice set of difference equations which you have to solve. And for lucky enough, jointly with Zhdanov, to discover using this formalism, this principally new class of special functions of hypergeometric type, which of course very, very complicated mathematical thing, which I don't want to say anything here about. Okay, so there are many open, complicated mathematical and unexplored physical applications. Thank you for the attention.
Okay. Thank you very much, Professor Spiridonov. Slava, very nice talk.
Okay.
Very, very nice talk. Yeah.
It's open for now comments and questions. So please go ahead and ask your questions. Yes. Okay, if not, let me start. Slava, I had two questions.
Go ahead.
Yeah. First question was your first part of the talk about the coherent states.
Yes.
Which you sort of generalize the coherent states. That's a very nice idea. Mm-hmm. I was wondering whether the general states essentially correspond to the squeeze states or something more than squeeze states.
No, these are not squeeze states. These are superpositions of canonical coherent states. And just a moment, I will just show you where squeeze states appear. Yes. Okay, squeeze states appear at the level of minimizing the uncertainty relation. So if you take, no, this is not yet. Yeah. If you take this minimal uncertainty principle, yes, then these coherent states, they minimize it. Both delta x and delta p are minimal. However, the product is minimal for squeezed coherent states, which differ from these ones by scaling the parameter variable x. If you take the coordinate x and scale it, then you get squeezed states essentially. Okay. And this squeezing is realized by different type of operators, not when you have exponential of quadratic combination of A and Eiger. So it is different from the squeeze states. And
so for your generalization, Slava, for your generalization, delta x, delta p therefore is greater than half?
Yes.
Oh, I see. I see.
Yes,
okay. Okay.
Minimization of this does not fix uniquely the canonical coherent state.
Okay.
The squeezed state also satisfies this minimization, or yes, that the product is 1/2.
Yes.
And so they are more complicated.
Okay.
You can impose additional constraints so that these states will be singled out uniquely, but that's additional constraint.
Okay. My second question was about your when you talk about these finite gap potentials.
Yes.
Yeah. It is also, yeah. I was wondering, it is well known that this potential minus n into n plus where dn square of x and m, where dn are the Jacobi polynomials. Are this, you are referring to the same or some other potentials?
Say it again about the potential. Because
the finite gap potentials which you mentioned,
yes,
is well known in the context of KdV that these finite gap potentials are minus n into n plus 1 dn square of x and m.
Yes, it's a elliptic potential. Yes, exactly.
Yes. So your finite gap potentials are the same or they're more general than that? They
are much more general. Essentially, the case you say, it's called Lamé equation case when you have a special type of band structure and the special potential. Let me say you simple thing. I will say you what is the most general finite gap potential.
Okay.
For them, you can find the explicit form of the potential. That's an important thing. That's why these potentials are exactly solvable. Let me see. Aha, here it is. I need to say about these things as follows. So, if you parameterize your potential in the following way.
Yes.
So your minus second logarithmic derivative of tau function. This is called tau function. This is the potential. This is tau function. So for finite gap potentials, this tau n is the Riemann theta function. For those potentials you mentioned, it's just Jacobi theta function, which determines you the potential. And in this case, it's Riemann theta function, whose for special choice of matrix of quasi-periods and for special choice of exponentials which enter there, analogs of the x. You see, Riemann theta function depends on, say, g-dimensional Riemann theta function. It depends on g number of coordinates when x is not one, but g of them. And you have to choose in a special way. You have to essentially take the linear section of that n-dimensional, g-dimensional space. And this is the general form of the finite gap potential. You see, it's much more complicated. It goes to Riemann theta functions.
Yeah, okay, thank you.
Yeah, I have a couple of questions, Professor Khare.
Yes, Prashant. Okay. Please go ahead.
Yeah, Slava, this Fourier transform what you got,
yes,
sum of 4 terms, they look like special Kitten states. Can I take a look at it?
Special, which one state?
Kitten. Cat, then kitten, baby cat.
Kitten. Yeah. I see, kitten. Small cat.
They are actually useful for quantum metrology. Let me just take a look at those states.
Yes, quantum metrology, you mean?
Yes.
Okay, here it is, explicit form. Just a second. Oh, here it is.
Yeah. Yeah, in fact, they are actually phase displaced cat. See, kitten state is of this type: alpha plus minus alpha plus I alpha plus minus I alpha. But in principle, you can have other kind of phases. So you are having different kind of phases here, right? 8 roots of unity, isn't it?
Yes. It's different. I looked the literature. I saw a combination of 4 cats with the signs, as you say, I and plus. That's true. But this one I did not see. But it's of a similar type. Yes, you're right.
But I'll take a look at it because I say there is a paper. It started from the paper of Jurek, the Nature paper, where he showed that these kitten states give rise to something called sub-Planck structures, very useful for quantum metrology. People have done experiments last year. So I will forward you some of those papers and I will take a look at this paper. Have you looked at the phase space within a function?
No, I didn't investigate them. As I said, I was working in a completely different field. And just last year, there was a chance that I returned back to this subject and finished my project.
Okay. I just had an optics letters paper just 2 months back on these kind of things. Maybe I'll forward it to you.
Yes. Sorry, I don't know. Who are you?
I am Prashant Panigrahi.
Prasanta. Yeah, so I could not understand it. It sounded as if someone different. Okay, very nice. Then Prasanta, I'm waiting for you.
Yeah.
Sorry about that.
No problem, no problem.
Okay, any other question?
Yeah, I have a couple of more questions.
Yeah, Prashant, please go ahead.
See this other one, that KDV.
Yes.
So they are, okay. So you are saying that they're related to quantum group, that Q parameter is like quantum group.
Yes.
Okay.
That's true. So essentially, if you wish, I can realize these quantum group actions on the soliton states of KDV, but you have to have an infinite number of solitons.
Mm-hmm.
And algebra is over here. Yes, that's the algebra. And for n equal 1, this is just the Q harmonic oscillator algebra. That's very nice and well known.
Okay.
Yes, Prashant, another question? You had some?
No, I was basically asking, that algebra A dagger minus Q A dagger A, if Q is real, there is that actually gives rise to, the so-called infinite statistics, when you construct these eigenstates, this A dagger minus Q square A dagger A equal 1.
That's right.
Infinite statistics, in the sense that all the states are normalizable. It is that O.W. Greenberg's paper, PRL paper, which we had done some work also. So actually it gives rise to, this corrected Boltzmann statistics. The statistics.
I see. Corrected Boltzmann statistics. I see.
So there must be some very deep connection with this.
Perhaps. I cannot comment right now for a reason that I stopped working on this type of quantum algebras long ago. And then barely remember now the details, and somehow prefer not to comment or whether to say how it should be, because I simply it's not in my memory now.
Okay, that's fine.
Yeah. Okay, that's all. Yeah.
That's it, Prashant. Anybody else has any other question, please?
Still, I want to add to my talk one simple thing, which just to take a few minutes. Maybe that raises more questions.
No, it's fine, Slava.
Yeah. So if you look, so you rewrite your potential through the tau function, and Hirota has found the expression for this tau function, for solitonic tau function of the following form. He just formally found this expression, sum over sigma i's, all types of sigma i's from 1 to from 1 to n, yes. And these are the phase shifts of the solitons, having this explicit expression, and these are these combinations of soliton energies with times x and so on. And it's amazing. It was done in 1971, and only in 1996, jointly with Igor Lutsenko, we have said that this is nothing else than the tau function. This is the partition function of the Coulomb of the gas, the lattice gas.
I see.
So essentially, the potentials, soliton potentials, and all the potentials actually which I was describing, just with different interpretations, all of them have the meaning through this tau function, as they determine the partition functions of the grand canonical ensemble of the Coulomb of the lattice gas, say unidimensional, which is written here, or Ising chain through very simple transformation, or two-dimensional Coulomb gas if you take these coefficients complex. So if you take these Ki complex values, then this is the partition function of the grand canonical ensemble for the two-dimensional Coulomb gas. That's the subject which I skipped, but it's also very rich and it sits inside of these things. So there is a very good output to the statistical mechanics actually behind this factorization method, the solitons, and so on, the integrable system. So that's what I want to say.
Raising the kind of connection.
Yes.
Yeah.
And you can compute the things. You can compute with this interpretation. You can compute the thermodynamic limit and find the thermodynamic quantities for these Coulomb for these gases. And for instance, one formula is here. So you get in this way for n equal 1, which is Q-harmonic oscillator. The realization of the Q-harmonic oscillator on the infinite solitone potentials, you interpret it as the this tau function is the partition function of a particular Ising chain with non-local exchange. And you can compute this magnetization. And it has very explicit, nice formula. So you see, this is the magnetization in that model. And it's obtained through the interpretation as solitone physics. And so if in factorization, this Q-harmonic, in this formula, that Q-harmonic oscillator appears through the real model of the non-local Ising chain on the one-dimensional lattice. So that's physics output, essentially. One of the physics outputs of those Q self-similar potentials.
Okay. So
I just wanted to inform Slava. Slava, these things would be put on the YouTube. So if you have some objection, we can hold it back.
YouTube, which things?
You know, the talk.
Your talk.
All the talk materials have been put up in the YouTube. Suppose if you want to change it or you want to hold it, so that only portions of it you would like to release, you can mention accordingly, we'll do it.
Well, the slides are okay, but the talk maybe not that good because it's very hot here. I guess you have more high temperatures than we do, but for us it's very unpleasant. So
yeah, so that's not a problem. Because the students are viewing it, so not a problem.
All right. Okay. Fine. So if there are no other questions, comments, so let's thank Professor Spiridino for an excellent talk. And it's a pleasure. And hope we can hear his talk again sometimes. Yes. Thank you, Slava.
Okay. Thank you for the attention and invitation. It was very nice to talk to you again.
Yes, I know. Okay, bye-bye.
Bye-bye.
Okay, bye, Slava.